Perfect. So my talk is about learning new behaviors and adapting skills to new situations. Let me start with the oldest dream of robotics, right? This is from the 1969. This is the first commercial of the first industrial robot ever. And they were so cocky back then that they already created a commercial showing this robot in the home of people doing all the tasks that you would like to do. And the amazing part is, you'll see in a moment that this robot really doesn't look at all like you would like to have it in your home. But the amazing part is that in the end, they were programming it pretty much like we program most industrial robots today. So move a little bit up, move a little bit to the side. It all fixed, pre-programmed, and with a sufficient accuracy to handle the environment. Now, as a society, we've totally moved on. The housewife sitting at home doing her nails while the robot takes care of her. The husband leaving for work. Well, that's all history, I guess. But we are by no means there to have these robots. So, and today it would be just as easy as back then to stage this, to program the robots to do exactly this task. But how do you actually get them to do tasks do this in a real world scenario? And the next question you should be asking yourself is, so where have robots been successful? And well, obviously industry, since in car manufacturing, it's very clear you can follow the same trajectory with a robot and up to 150 micrometers. And as long as everything is perfectly synchronized and timed, you will never have any problems. And yes, there's several millions of such robots, and there wouldn't be any car manufacturing, neither in Japan, nor in Germany, nor in France today if it wasn't for robots. Then, of course, things like the lawnmower, where the lawnmower basically follows the wire and the ground. And anybody who's ever owned a Roomba knows the first thing you do when you buy a Roomba is, well, or any vacuum robot, you arrange your furniture such that the robot doesn't get stuck under the bed. So with other words, in robotics, we're typically successful when we adapt tasks to robots. Now, let me contrast to you the classical robotics worldview, and that's really the worldview in the world where, well, I grew up when I was a university student, and when I started my PhD in robot learning, people were very much adhering to this worldview, and they basically said, oh, you need to do classical robotics, and analytical robotics basically needs just three components. First, we know physics, so we can build an accurate forward model. And it's really true. You can create really, really good physical models, and they give you great simulators. And in the end, you do have a great prior for simulation. Then they basically said, well, you need a good planning algorithm, and voila, you're done. But unfortunately, planning, of course, is super hard because it has an exponential explosion of states, and replanning online has remained as hard as it used to be. And finally, fast feedback control, which is unfortunately, well, which has the big advantage of killing all the errors you have during execution, but at the same time, it has really withheld us in robotics, since we've built robots now to be stiff, power hungry, and complex, just so that we can control them with the classical methods. With methods which basically, well, want us to follow trajectory perfectly without incorporating any sensing. Now, that was very, very true 10, 15 years ago. And now, basically, well, we've had a big shift, right? If you go to a robotics conference today, it's so much of it is about deep learning. And in the end, there is a ton of people who now, back then they used to make fun of me for wanting to do robot learning. Now these days, it's everybody wants to do deep learning for robotics, and it's all deep robot learning. But it has gone to the opposite extreme. Now we basically say, oh, we don't need any structure, any physics, any knowledge of the world, just a flexible representation with suitable algorithms. And unfortunately, we end up getting extremely bad, physically implausible solutions, huge optimization biases, and well, we get solutions I would never trust to do robot surgery, for example, at all. The second thing they ask for is lots of data. And robots live in real time. and yes, you do get a lot of data which is useless. So like all the intermediate points of your trajectory you get during an arm movement, but these are in the end useless points. But you only get very, very few episodes of what actually matters. So with the result that, well, we typically have to figure out how to create data better. And the best answer so far we have in deep learning people bring up is, oh, why don't we just use the physics simulator as data generators? But then the big question is, aren't we all back to square one? And finally, well, lots of computation. And well, that again throws out all the important robot learning components about online learning, energy storage, if you want to really learn on the robot, what to learn and what kind of communication problems you do have. So how should robot learning differ? Well, ideally, it is much more human-like. It learns on the real system. It adapts online without replanning and maybe not always achieving the optimal solution, but a good one. Avoiding the real-time bottleneck and especially cope with the, well, little episodic but much real-time data problem. And be partially explainable and physically plausible, as well as, well, coping with a simulation optimization bias. And finally, we really got to build bodies which are more human-like, more energy efficient, more squishy, more higher acceleration, more versatile, instead of building these stiff bodies which are suitable for feedback control. And obviously, I don't have the solution, but I have some good lessons from the last, well, 15 plus years. So this brings me to my research questions, and I'm pretty sure I'm not going to be able to even go into all of them, given that I have basically 12 minutes left. But let me give you a little bit of an overview. The first thing I think we really need to bring back to robot learning is, how can we learn from little data? And well, that brings us to the objective of all robot learning. In the end, all imitation learning, we want to reproduce then state action distribution, where QSA is the state action distribution which we have observed. We want to reproduce it with a policy, meaning a distribution over actions given the state, and well, which induces typically a state heat distribution. Now, this here is one of the oldest ideas of how you should do robot learning. In fact, it dates back to Mitchell Chambers or Claude Sammet. Mitchell Chambers are from the 1960s, Claude Sammet from the 90s, who introduced this idea of, well, behavioral cloning. Now, in recent years, we typically figured out that you need to bring in more prior knowledge. So we want to have more assumptions on the policy, like, for example, the way state distributions propagate when you apply the policy to the state distribution. Now, this is actually a relatively recent development to do this in such kind of optimization problems and still stay in the machine learning framework. I think Peter Englund's work is, for example, one of the earliest example of such kind of model-based behavioral cloning. However, its dual of inverse reinforcement learning was, of course, the big hype of the early 2000s and the early 2010s. Alternatively, you could also just try to solve the dual problem just for minimal physics and obtain, well, a good kind of a policy class. And the interesting part is, unless you do some really smart assumptions, the dual is actually harder than the primal. Now, let me show you a few examples of where this was applied. One is so where the primal was applied. One is here the learning of motor primitives. Yes, in this case, we have a ball on a string, and this was literally learned out of the box, and well, the system acquired it, and we were actually surprised how fast you could acquire such a acquire this, given that hand programming of it didn't work after half a year, at least not in such a reliable and stable way. You can learn also you can also learn, for example, basic table tennis is by just taking the robot by the hand and showing it a few trajectories, and then well, run again the same kind of model-based behavioral cloning. This is work of Sebastian Gomez, who showed that you can basically cover the full forehand range by just 6 successful demonstrations. So the next important part, of course, is we want to have self-improvement. And for self-improvement, we do need reinforcement learning. And this is one major disadvantage, since now we're replacing this f function of similarity function in the objective by an arbitrary score r. And when you look at this, even when you bring in the same policy assumptions in addition, this is becoming a really, really hard problem. Since now we would have here a linear dynamic programming problem, and yes, it has a dual, and this dual is harder than the primal. And yes, you could now run things like optimal control and or well, classical dynamic programming on it, try to solve the Bellman equation. But in both cases, you are actually surprisingly stuck. First, because the primal is so the linear programming, so the solution at the bottom is much harder than the solution at the top, and this again, well, brings up a big conundrum, since we now have here no real notion of data, but we would actually much more like to solve the upper equation than trying to approximate the lower equations based on data. So with no natural notion of data, well, we can actually make use of transferring the policy similarity constraint from behavioral cloning. And well, together, this gives us actually a general framework for deriving reinforcement learning algorithms. It's by now 10 years old, but surprisingly, all of the currently modern algorithms up to TRPO, soft actor critic, and you can name them, all the entropy regularization approaches direct results from this framework. But this framework is much more principled than many of the approaches we see today. Now, Jens Kober was the first to apply it, and here you see his learning of imitation learning. He starts with an imitation learning solution, then subsequently, well, the robot self-improves, and typically after 40-something trials, the robot actually gets the ball into the cup for the first time. It can't reproduce the accelerations of the human, and it has to first learn its hand-eye coordination. So that's why it obviously can't just work with the one demonstration. And after 40-something trials, it gets the ball into the cup for the first time. After about 90 trials, it typically becomes perfect. And well, here you see improvement. Well, so we asked, how does it compare to humans? It turns out that, well, 8 to 10-year-olds managed to not learn it at all. The 10 to 12-year-olds learned already within 30-something trials, and grown-ups take 3-4 trials. So it seems to be only me who took half a year to actually obtain this behavior. Now, next thing, of course, is you want to use such algorithms, and instead of using one black box or gray box policy, you really would like to use as much of the structure of the world as possible. And that basically brings you to something which is closer to a white box model, where there is a supervisor, primitives, and some form of execution. Now we're quickly going to at least say something about the supervisor and the primitives. So we build parsers, which can then get you complete libraries of primitives using NEM-like algorithms, which iteratively takes trajectories, segments them, builds a library, explains the segmentations, and finally can deliver you, well, execution candidates for the behaviors you have observed. And we've applied this in a variety of settings. One of them was robot table tennis, where you would then really learn modular policies that enable you to, well, let me skip this part because we're running low on time, which allow you to incorporate both the user and the robot, so both the opponent and the robot, and play a basic game of table tennis. Or learn things like sequencing movement, including things like block stacking, doing a pepper mill, or here at the bottom, fast forward this a bit, the task of cutting an eggplant. Now this shows you that we can build behavior and by learned systems, and by having such kind of a, well, primitive built white box model, but it still opens up the big question of how we should do better execution. And that is actually the point where we have tons of data. So it's really quite the opposite of the scenario of learning tasks. Since if you want to learn execution, you have a continuously arriving stream of data, and this data is not IID; it's actually trajectory based. But it's really hard to it's really hard to learn with it online in real time. And ideally, you want to have physically plausible solutions. Now, it turns out that three things had been tried a lot in the past. I mean, obviously, every engineer likes to cut his robot apart and does model engineering and perfectly identifies the center of gravity, inertia, and so on. And this works obviously when you can take your robot apart, but it doesn't work in general. On the other hand, when you look at people, well, a lot of people have suggested to do system identification, which turns out to be surprisingly hard when it comes to high-dimensional robots, since most of the time, well, the parameter set here is non-unique and there are constraints on it, and it's actually not so easy in the end to get a really, really good inverse dynamics model, for example, or parameter identification, despite that physics by mechanics is linear in the parameters. And finally, there's been black box learning, which said like, oh yeah, let's just take an arbitrary neural network and learn a well forward or inverse model. Now, all of these approaches have their shortcomings, since the first one you have to take the robot apart, and the second one you frequently get a physically non-plausible model or not even a good model at all, because this is a very highly over-constrained problem occasionally when you have noisy data. Or in the black box model, you can't learn an energy model at all. And additionally, you can also you're typically not physically plausible. Now, Michael came up with the idea of creating special neural networks called deep Lagrangian neural networks. And these have enabled him to learn both forward, inverse, and energy models. This really makes a huge difference. At the left, you see the analytical robot, the analytical model, perfectly done, and it obviously is capable of doing the job out of the box. You see system identification online in real time. It never gets the solution. And you can see a D-line neural network, which does a perfect solution. And this also works for learning the physics of complete robot arms during control quite well. Now, let me come to the last point really quickly. I just want to make the point, you don't want to build robots which are stiff and clumsy. You really would like them to be like humans. That means we have to abandon classical design principles and have robots to have better bodies. And well, for table tennis, we actually did this. And sorry. This is the result when you let actually a robot give it nothing initially, and you let it run for 14 hours. And for 14 hours, it hit initially just the air, and in the end, you see it actually gets really good table tennis behavior. And all of that purely from learning, purely from interacting with a muscle-based system of pretty high complexity, but this time with high accelerations and absolutely no prior knowledge. Alrighty, with that, here are my lessons, and I'm sorry for, well, being exactly on time according to my watch.
Thank you for your great talk. Yeah, we have time, I think, for a single quick question. I actually have one because to me, naively, a demonstration for robots is like helping it reduce the exploration space and focus on part of the space. And so somehow, naively, is it the key element that is required? And for example, anything about transfer learning or policy that you prior policies, a way to reduce this exploration space, or is there something more needed about representations that needs to be acquired? Model learning.
A little bit of both. So we typically constrain our learning systems so that they actually can only learn mechanics. So that's I think, a very, very important constraint. So that they will not learn, well, systems which are not second order systems, basically, when you combine the complete body. And that is typically quite good knowledge you can give them. this is something we would encode into the representation of the motor primitives, for example, if we learn primitives. Another thing we would typically, well, if you don't want to constrain anything, then you have to actually learn a model, like in the last, but it turns out that working with models generically, well, is at the moment generically harder than sampling the hell out of the real world. And that's so learning table tennis from scratch was actually on the real system. So the key thing was to build a system which was sufficiently reliable and not self-damaging so that you could actually allow it to do gigantic accelerations, hit it wildly around itself for 14 hours until it finally would hit the table tennis balls. Initially just did this, like we gave it some motor babbling. And then, yeah, I should have shown that part of the video still, but I noticed I ran out of time and we are 2 minutes above now. And Stefan looks already quite eager to start.
Yeah, so I think this model learning issue is really critical. I hope we have further time to discuss it tomorrow.